Hello everyone, I hope all of you are doing fine. In the previous video, I showed you the power of cuDF, that is a CUDA data frame. How a CUDA data frame can be utilized efficiently for generating insights. This video will show you the power of cuML and how you can create some amazing machine learning models quickly at scale using a GPU. So without wasting any further time, let's kickstart the video. The first activity that I'll do is I'll import all the necessary modules. So as you can clearly see, there are tons of necessary modules that are required in this activity. So I'll go forward and import all of them. Now the next thing that I'll do is I'll take the data_proc.csv file which I had generated in the previous example, and I'll read it using the pandas read csv command. So let me go forward and read the file into a data frame df. So the overall time taken for the read operation for this particular data_proc.csv file is around 9 seconds. At the end, it clearly signifies that the total number of rows in my data frame are around 3 million and we have close to 31 columns. Let me now go forward and show you the first 5 rows of the data frame. Now let me go forward and remove any rows with empty values or missing values. So let me go forward and call the drop_na function. In the entire exercise, my dependent variable is severity. I want to now check how my severity column is distributed, which is where I'll call the function value_counts. So let me go forward and run this cell. So as you can clearly see, there is a clear class imbalance where class 1 has only 26,000 samples, whereas class 2 has around 2.5 million samples. So this is something that we'll have to handle going forward. What I'll do next is I'll kind of try to separate out the majority and minority class samples. So let me go forward and do that. In order to separate the majority and minority classes, what I've done is basically I've used referencing in a pandas data frame. And what I've done is I've created individual pandas data frame like df_s1, df_s2 and so on and so forth. So let me go forward and run this cell. Rather than using oversampling and creating a larger data set, what I'm doing right now is I'm going forward and creating an undersampling based model. The reason is very simple. I don't want the same data points to repeat again and again, which is where I'm kind of using undersampling as compared to oversampling. So the first thing that I do is I count the minimum number of rows that are present in either of the data frames. So which in our case would be in df_s4. So which is something that I've achieved using this piece of code, which is count is equal to min of df_1.count and 0. So essentially I'm going through all the rows in the different data frames and I'm figuring out which data frame has the minimum number of rows. So that is something that I'm achieving using this piece of code. Now the next thing that I've done is basically resampling. So if df_s1 has close to 2.5 million rows, I only want 26,000 or 27,000 rows, which is what I've achieved using the resample function. A similar activity is what I've done for df_s2, df_s3 and df_s4. Now the first thing that I do is I want to concatenate all the data frames into one. So which is where first I concatenate 2 at a time, which is where I create a data frame df_s12. Similarly, I create a data frame df_s34. And finally, I combine the two other data frames, that is df_s12 and df_s34. Now if I basically do a df group by in the severity column, which is our target column, and do a count, I can clearly see that all the classes have 26,000 samples. So the entire distribution is equally distributed now. So now that we have an equally proportional representation of each classes, let's go forward and create machine learning models. Before we jump and start the machine learning model creation activity, the first thing that we'll have to do is basically convert all our string columns into numeric, which is where I'm using an ordinal encoder. The reason why I'm using an ordinal encoder is because of the data that is present. So by fitting all the columns which are say object type or string type, I'm kind of encoding them through the ordinal encoder. My Y column is basically the target column, so that is also something that I've done in this piece of code. So let me go forward and run this cell. Now let me go forward and split my dataset into training and testing. I'll be using 70% of the data for training and 30% of the data in testing. So let me go forward and run this. Now I'm using a very simple classifier for this activity, which is the k-nearest classifier, where I've set the total number of neighbors to be equal to 3, and I fit my data, that is my training data, which is xtrain and ytrain. So let me go forward and run this cell. So the entire activity in terms of fitting the data was very quick. Let me now go forward and show you the score on unseen data, which is our testing data set. So the overall accuracy of the model is close to 54.49%, and the entire process took around 5 minutes and 52 seconds to give out the results. So it took a long time for validation. However, the training or the fit process was very quick. Now if I have to carry out the activity in record time, which is where our CUDA data frame would come into picture, and cuml based libraries would also come into picture. So let me now go forward and convert our xtrain, xtest, ytrain and ytest values into their CUDA data frame equivalent. So the way I would do that is by calling the function cudf.dataframe.from_pandas. So the entire process was really quick. The entire conversion took around 5.7 seconds. Now when I call the k-nearest classifier and I pass in 10 neighbors, not 3 this time but 10 neighbors, and I want to carry out the same activity using a GPU, let's see the overall time taken. So the entire process takes around 435 milliseconds. Now this is in line in terms of the magnitude with what the CPU was taking for an Sklearn based equivalent model. But here the GPU has just started. So it takes a while in terms of GPU to initially start and then create something out of it. So if I do the same activity again for the second time, the process would be much more quicker because the GPU would be in the active state. So that is one of the reason. The second reason is the k-nearest neighbors, or the number of neighbors that I have defined here, are 10 as compared to 3. That is where the small additional calculation would kind of take a bit more time. But now if I want to validate how good the model is performing, which is where I'll call the knn.score function, pass in the xtest and ytest values and essentially the CUDA data frame equivalents. So let me go forward and run this. Now this was super quick. The model is around 55.6% accurate, like you've increased 1% accuracy, but the overall time is still in milliseconds. On the other hand, the CPU version was taking around 5 or 6 minutes for validation. Here it was super quick. The reason is again simple. The GPU is in the active state currently, and once I run the GPU in the active state, then essentially all the compute would happen very quickly, given that you've already initiated the GPU activity. So this is something that I wanted to share with all of you today. I wanted to give you a glimpse that you can create machine learning based models on GPUs using cuML. If you're thinking of getting an RTX laptop, then NVIDIA is also providing an amazing opportunity for students. If you purchase an RTX laptop, then you can avail a deep learning instructor-led certification course from Deep Learning Institute, which will give you a head start in your deep learning career. For more information, I'll attach the link in the description section of the video. Do check it out. Well, this is all that I had in today's video. I hope you found today's video informative. Thank you so much for watching the video.